Dear viewers, welcome to Finite Element Analysis. Example problem of one-dimensional Trusses problem. Trusses is the combination of the member. It will create the rigid structure. The example problem for two-bar truss shown in the figure. Determine the displacement in the y direction of nodal point 1 and the axial force in each element. A force of P equal to 1000 kilonewton is applied at nodal point 1 in the positive y direction, while node 1 settle an amount of delta equal to 50 in the negative x direction. Let Young's modulus 210 gigapascal and area A equal to 6 into 10 power minus 4 meter square for each element. The length of the element are shown in the figure. The dimension all are in meters. Node 1, the element 1 connected with nodal point 1 and 2. Element 2 connected with node 1 and 3. The node 2 and 3 is fixed support. Nodal point 1 is roller support. The direction x and y axis is shown in the diagram. Here is the coordinate length of the element 2 is 4 meter. Then trace in between the fixed support is span length of 3 meter. Normally, we are using stiffness matrix formula is K AE divided by L square LM M square minus L square minus LM minus LM minus M square minus L square minus LM L square LM minus L minus M square LM M square. This is for stiffness matrix for one-dimensional truss problem. The L is based on the coordinate system. The node point 1 is x1 y1, node 2 is x2 y2, node 3 is coordinate system is x3 y3. So based on this, L is we can calculate it by two way. One is based on the theta orientation with respect to x-axis or y-axis. L equal to cos theta. The cos theta is x2 minus x1 divided by LE, the length of the element LE. M equal to sin theta, that is y2 minus y1 divided by LE. The LE is root of x2 minus x1 square plus y2 minus y1 square. In this problem, first we have to determine the length of the element 1. Length of the element is not given, so we have to using the theorem trigonometric. The root of 3 square plus 4 square equal to 5. In this problem, we are going to using the sine conversion theta we are going to use. We are not using for the coordinate approach. So formula for stiffness matrix element A is then row 4 cross 4 row matrix. Area is given is 6 into 10 power minus 4. Young's modulus is 210 gigapascal. Substituting the value of area and Young's modulus 210 power 6. Then length of the element is 5. We have to calculate the theta value with respect to x-axis. X-axis is cos theta equal to dimension is y by x, that is x here is x direction is 3 divided by 5. Similarly, Sin theta we have to calculate. The notation I am using CNS equal to 4 divided by 5. The value is 3 divided by 5, 0.6. S is 4 divided by 5 equal to 0.8. Substituting the value in this stiffness matrix for element 1, C 0.6 square is 0.36. Similarly, C into S 0.6 into 0.8, 0.48. CS 0.48, S square 0.8, so 64. So similarly, we have to calculate and substitute this value of the stiffness matrix value for element 1. The next step, we have to calculate the similar way of to stiffness matrix for element 2. The element 1, the AE divided by L, we have to simplify the value is 25,200. The element 2 is connected with nodal point 1 and 3. So based on this orientation, the theta value is 90 degree. So element 2, C value is C cos 90 degree. So 0. S equal to sin 91. Substitute the value in the stiffness matrix for element 2. So substituting the value is A E divided by L. Simplify the equation. We can obtain the value is here is 25,200. So where simplicity of the equation element 2 is written in with the same factor 25,200 in front of the matrix element 1. So superimposing the element stiffness matrix equation element 1 and 2. So we have to simplify the inside the matrix of so 1.25. Now we determined stiffness matrix for element 1 and 2. Then rewriting the equation of stiffness matrix element 1 and 2. Write down the degree of freedom. So nodal point 1 will be have two displacement u1 v1. Nodal point 2 is displacement u2 v2. Similarly, nodal point u3 v3. So element 1 is connected with node 1 and 2. So u1 v1 u2 v2. The element 2 is connected with node 1 and node 3. So u1 v1 u3 v3. The next step, we have formulate the global stiffness matrix, adding the stiffness matrix element 1 and 2. So we obtain the global matrix K, related the global force to the global displacement Y. Now the standard equation for determination of displacement K row matrix U displacement vector equal to F force vector. Carefully reassemble the value of stiffness matrix for element and element to corresponding row and column. Then finally simplified the values. The next step, we have to identify the boundary condition. Node 1 is connected with roller support. Node 2 and 3 is fixed support. So boundary condition is u1 is given is delta, u2 is 0, v2 0, v3 and v3 is 0. We can again partition equation with known displacement, then simultaneous solve those associated unknown displacement. To do this partition, we consider the boundary condition, apply the boundary condition, then actually u1 known value, only we have to calculate the v1. So Based on this, remaining thing is displacement all are 0. So substituting the known value, then only one unknown we have to calculate. So only one equation we have to generate, then find out the v1 value. Substituting u1 0.05, v1 we have to calculate u2 0, v2 0, u3 0, v3 0. Then substitute the force vector value f1. The p is acting towards to positive direction given in the problem. So 1000 kilonewton. Then generate the equation is 25,200 into 0.8 into minus 0.05, 1.89 into V1 equal to 1000. So next 25,000 into minus 24 into 10 power minus 3. So we obtain the value is minus 604.8 plus 25,000 into 200 into 1.89, 47,628 into V1. So finally we obtain the V1 value is displacement at node 1 V1 is 0.0337 meter, where the positive value indicate horizontal displacement to the left. Next, we have to determine the local element force are obtained by using the equation. We can following that element 1. We know that C value and S value. C is 0.6, S equal to 0.8. The formula for calculating the axial force for element 1 is AE divided by L, rho matrix CS 00 CS, then displacement vector for element 1. Element 1 connected with node 1 and 2. So U1 V1, U2 V2. Substituting this value, so already we calculate AE divided by L 25,200. Then matrix of row matrix. Then subject 0, C is 0.6, S is 0.8. Substitute the value. Then substitute the displacement U1 V1, U2 V2 is 0. The performing the matrix triple product in the equation, yield of F1x equal to minus 76.6 kilonewton, F2x equal to 76.6 kilonewton. Similarly, we have to calculate for axial force in the element 2. The local element force are obtained by using this above equation alien. When the following substitute the value of AE divided by L, then row matrix. Here is C value is 0, S value is 1. Substituting the element 2 is connected with nodal point 1 and 3. So substituting the nodal point displacement 1, nodal point displacement 3. So U1 V1, U3 V3 equal 0. So finally performing the matrix triple product in the equation, yield is F1 is x equal to 1061 kilonewton, F3x minus 1061 kilonewton. The problem is asking to determine the displacement in the y direction of node 1 and actual force in each element. Summary of the result is displacement in y direction of node 1 V1 equal to 0.0337 meter. Actual force in each element 1 and 2 is F1x minus 76.6 kilonewton, F2x equal to 76.6 kilonewton. Element 2 F1x equal to 1061 kilonewton, F3x equal to minus 1061 kilonewton. In this video, we are known about the how to solve the one-dimensional stress example problem based on the coordinate system with respect to angle conversion based on the stiffness matrix. First determine the stiffness matrix element 1 and 2, then formulate the global stiffness matrix, then apply the boundary condition in the displacement vector, then apply the given value of force vector known value, then find out the unknown parameter value of nodal point 1 in V1 value. Then we are find outing the axial force of each element. Thank you for watching my video. Thank you.